In our last journey, we drifted through the silent depths of the cosmic dark ages, a universe without stars, without galaxies, without even a single point of light. For 150 million years, everything was quiet. Hydrogen and helium floated like a cold mist, settling slowly into the invisible gravity wells carved by dark matter. Then, after ages of waiting, something extraordinary happened. The first clouds cooled, collapsed, and ignited. Enormous, brilliant population of third stars burst into existence, flooding the darkness with ultraviolet fire. Their lives were short but spectacular, ending in titanic supernovae that scattered the universe's first heavy elements. From these explosions came the seeds of everything that followed. The earliest galaxies began to take shape, chaotic, clumpy, and glowing with bursts of new stars. Black holes were born in their centers. Reionization swept across the cosmos, turning opaque gas into a transparent sea of light. Now, we move forward. The universe is no longer young and silent. It is restless, changing, and learning to build on grander scales. In this episode, we witness how those early sparks grew into the first cosmic cities, the galaxies that will shape everything to come. For the first time since the Big Bang, the cosmos has awakened. Not all at once, not with a sudden blaze, but slowly, carefully, like embers scattered across an infinite field of black velvet. These are the scattered children of the first stars. Population mimic giants massive, blazing, brief. They pierced the cosmic dark. But they did not last. Most lived only a few million years. Then they died violently, spectacularly, seeding the universe with something it had never known before. Heavy elements, metals, the ashes of stellar fire. And in those ashes, the seeds of something far greater than any single star. The universe was about to learn how to build cities. The death of the first stars was not an ending. It was a transition, a handing of the torch from individual brilliance to collective structure. For hundreds of millions of years, the universe had been dominated by individual giants. Lonely beacons scattered through the void. But now, something fundamental was changing. The scattered points of light were no longer isolated. They were beginning to interact. TO combine. TO build upon each other's foundations. Think about what this means. A single star, no matter how massive or brilliant, can only influence its immediate surroundings. Its light travels outward, ionizing gas perhaps a few hundred light years away. Its supernova shockwave might propagate 1,000 light years before dissipating. But then it's done. Done brief flash in cosmic history. But when multiple stars form in the same region, something different happens. Their effects overlap. Reinforce each other. ET create conditions that persist long after any individual star has died. The first supernovae had enriched the gas around them with heavy elements, carbon, oxygen, silicon, iron. These metals spread outward in expanding shells. And when these shells from different explosions collided, they mixed, creating larger regions of enriched gas regions that now had different properties than the pristine hydrogen and helium that dominated most of the universe. These metal-enriched regions became the preferred sites for the next generation of star formation. Because metals change everything about how gas behaves. They allow it to cool more efficiently, to O collapse more easily, .O fragment into smaller pieces. And so the second generation of stars began to form, not in isolation, scattered randomly through space, but clustered together in the same regions where the first generation had died, building on the foundation that had been laid. This is how structure begins to emerge, not through careful planning or design, but through a simple feedback loop. Stars form. They enrich their surroundings. This enrichment makes it easier for more stars to form nearby. Those stars further enrich the region, and so on. But there was another factor at work too, something invisible but absolutely crucial. Dark matter. We've talked about dark matter before. The mysterious substance that makes up most of the matter in the universe. It doesn't interact with light, doesn't collide with normal matter except through gravity. But that gravitational interaction is everything. Dark matter had been collapsing into halos since the earliest moments after the Big Bang. Small halos at first, just a few thousand or million solar masses. But these small halos were constantly merging, combining into larger ones, building a hierarchy of structure from the bottom up. And wherever dark matter concentrated, normal matter followed. Dihydrogen and helium gas fell into the gravitational wells created by dark matter halos. Accumulated there. Compressed. Heated through gravitational energy. And eventually formed stars. ZO, distribution of first-generation stars, wasn't random. They formed preferentially in the densest dark matter halos. And when they died and enriched their surroundings, that enrichment happened in and around those same halos. Now, as the second generation began to form, they were drawn to those same locations. The deepest gravitational wells, where dark matter was most concentrated, where previous generations had already enriched the gas, where conditions were optimal for star formation. This is the beginning of proto-galaxies, not yet galaxies in the full sense, but concentrations of stars and gas in dark matter halos, regions that would, over time, evolve into recognizable galactic structures. The cosmic web was starting to make itself known. That vast network of filaments and nodes that defines the large-scale structure of the universe. For the first time, it was becoming visible, not the dark matter itself, which remains invisible, but the light from stars tracing out its architecture. DGS was flowing along filaments, channeled by the gravitational influence of dark matter, streaming from lower density regions toward the densest nodes. And where multiple filaments intersected, where the gravitational potential was deepest, the most massive proto-galaxies were forming. Small halos were merging into larger ones. Each merger brought more mass, deepened the gravitational well, made it easier to capture more gas from the surroundings, creating a self-reinforcing cycle of growth. And in the deepest gravitational wells, where streams of hydrogen converged from multiple directions, something remarkable was happening. The gas wasn't just accumulating, doesn't it was beginning to organize. WTO shows signs of structure beyond random chaos. The universe was preparing to create its first true galaxies, places where millions or billions of stars would orbit together, where gas would cycle through repeated generations of star formation, where black holes would grow and shape their surroundings, where chemistry would evolve and life would eventually become possible. But this transformation wouldn't happen overnight. It would take hundreds of millions of years, require countless mergers and interactions, demand the death of billions of stars to enrich the gas sufficiently. The first light had been struck. But now came the hard work of construction building the cosmic cities that would define the universe for the rest of its history. Look up at the night sky. Every galaxy you can see, from the nearest dwarfs to the most distant spirals, began in moments like these. Diem te chaotic mergers of small dark matter halos. Diem me memortes the garden, the first supernovae. Diem the gradual organization of random stellar populations into coherent structures. Our own Milky Way galaxy traces its lineage back to this era. Dotkin 5 years, Madlank Nacernovingly, this adventions became red. Forming its first stars, beginning the long journey that would eventually lead to the galaxy we inhabit. To the atoms in your body were forged in stars, but those stars formed in galaxies. And those galaxies began in the aftermath of the first stellar generation. Everything is connected. Everything has a history. And that history begins here, in the transition from individual stars to collective structures. The cosmic dark had been pierced by brilliant points of ultraviolet radiance. Now those points were beginning to cluster, to interact, to build something greater than themselves. The era of isolated first stars was ending. The era of galaxies was beginning. This was not a gentle process. The early universe knew nothing of tranquility, nothing of the ordered spiral arms we see in galaxies today, nothing of the calm, steady star formation that characterizes most modern galaxies. The first galactic formations were born in violent sin, chaos, din, storms that would dwarf anything we can imagine. Small dark matter halos collided constantly in these dense regions, each containing perhaps 1 million solar masses of hydrogens, sometimes less, sometimes more, but all of them small by modern standards. They merged, shattered, merged again, then in endless dance of gravitational interaction. When two halos approached each other, their dark matter simply interpenetrated, passing through without colliding, because dark matter doesn't interact except through gravity. But the gas was different. The gas has pressure. The gas can collide. When the gas from two halos met, it slammed together at tremendous velocities, hundreds of kilometers per second, faster than any wind on Earth, faster than any explosion we've ever created. This created shocks, regions where the gas suddenly compressed and heated, temperatures spiking to millions of degrees in an instant. These shocks, lit up in X-rays and ultraviolet light, brief but brilliant flashes marking each collision. If you could have watched the early universe in X-ray vision, you would have seen it flickering constantly. Thousands of these collisions happening across every patch of sky. But shocks don't just heat gas, they also compress it. And compression can trigger star formation. Behind each shock front, in the compressed, cooling gas, new stars began to form. Not one or two, dozens. Nothing Shumj small clusters igniting almost simultaneously. Go wide. Belen's galaxy formation was intimately tied to violence from the very beginning. Every merger brought a burst of star formation. Every collision lit up the gas with newborn stars. And all the while, the cosmic web fed them. This vast network of dark matter filaments stretching across the universe, invisible to light, but visible through its gravitational effects. DAS didn't just sit in halos, waiting to form stars. It flowed, constantly moving from lower density regions toward higher density ones, channeled by gravity along the paths of least resistance, which happened to be the dark matter filaments. These filaments acted like highways. Or rivers, perhaps. Streams of gas flowing from the voids toward the densest nodes where proto-galaxies were forming. And this inflow was crucial because star formation consumes gas, converts it into stars that no longer participate in the gas dynamics. Without a steady supply of fresh material, star formation would quickly exhaust the available gas and shut down. But the filaments provided that supply, a constant stream of hydrogen flowing inward, replenishing what was lost to star formation, keeping the process going. Some filaments were thicker than others, carried more gas. Karma's breaking shells had multiple filaments converging, creating particularly rich feeding grounds. What educate great feeling rich feeding grounds? UA's feeding grounds. Ditjau Angelikingsstra Asanaking. Karusen holding great feeding grounds. Hewing and Morgan now and if fry from God finals. And was every förmåga sharp för betrush with a kidda henset there. And in the places where 3 or 4 or more filaments met, where the inflow was strongest, the most massive proto-galaxies formed, the ancestors of the giant elliptical galaxies we see today. But the gas didn't fall in smoothly. It came in streams and clumps. Comes sometimes a large cloud would detach from a filament and plunge directly into the powers sometimes. The flow was more steady, like a river. Either way, when it arrived, it had to dissipate its kinetic energy. And the way it did that was through shocks and turbulence. Imagine a river pouring over a waterfall. The smooth flow becomes chaotic, full of eddies and whirlpools, spray flying in all directions. That's what the gas flow into proto-galaxies looked like. Supersonic turbulence. Velocities so high that the gas couldn't flow smoothly, couldn't settle calmly. Instead, it churned, created vortices that spun off and dissipated, generated waves that propagated through the gas and steepened into shocks. Magnetic fields made it even more complex. The gas carried weak magnetic fields with it from the intergalactic medium. As the gas compressed and turbulence twisted it, these fields amplified, grew stronger, began to influence the gas dynamics. Magnetic fields resist compression perpendicular to their direction, so they could slow down collapse in some directions, while allowing it in others, creating filamentary structures within the proto-galaxy, threads of dense gas threaded through lower density regions. and every few million years, a massive star would die, explode in a supernova, send a blast wave tearing through the entire proto-galaxy. These supernovae were like bombs going off in an already chaotic environment. The blast waves plowed through turbulent gas, compressed some regions, triggering new star formation, dispersed others, shutting it down temporarily, heated everything they touched to millions of degrees. In a modern galaxy like the Milky Way, supernova blast waves eventually lose their energy and fade into the background. The galaxy is big enough, massive enough, that individual supernovae don't affect the overall structure. But these proto-galaxies were small. A single supernova could blow a hole clear through them, inject enough energy to unbind a significant fraction of the gas. Gas was constantly being stirred, by infill from filaments, by turbulence from supersonic flows, by magnetic fields amplifying and twisting, by supernova blast waves from dying massive stars. It was. Beautiful, violent chaos. And yet, somehow, stars were forming. The galaxies were growing. Structure was emerging from the mayhem. Because even in the midst of all this violence, gravity never stopped working, pulling things together, deepening the potential well, making it harder for gas to escape. With each merger, the proto-galaxy grew more massive, its gravity stronger, its ability to retain gas despite supernova feedback improved. With each new generation of stars, more metals were produced, more efficient cooling, faster star formation. 8. It was a race, in a sense, between the processes that built structure and the processes that tore it apart, between gravitational collapse and feedback, and in most proto-galaxies, gravity was winning. Slowly, gradually, but winning nonetheless. The proto-galactic storms were violent, but they were also productive. Every collision compressed gas and triggered star formation. Every merger brought more mass and deepened the gravitational well. Every supernova enriched the gas and set the stage for the next generation. These were forges in the truest sense places where raw material was hammered and shaped, where impurities were mixed in to create alloys stronger than pure metals, where heat and pressure transformed simple ingredients into complex structures. And what was being forged? The first true galaxies. Not yet. Not quite yet. But soon, the foundations were being laid. The cores were forming. The gas was being enriched and organized. That was needed was time for the mergers to slow, time for the turbulence to dissipate, time for rotation to assert itself and impose some order on the chaos. But before that could happen, one more transformation was needed. The heavy elements from dying stars needed to work their magic, needed to fundamentally change how gas behaved, needed to open the door to a new kind of star formation. That transformation was already underway. The first metals changed everything. Everything. It's hard to overstate how important this was, how fundamentally it altered the trajectory of cosmic evolution. Before the death of population, AI stars, the universe knew only hydrogen and helium. These light elements were created in the Big Bang itself. Dihydrogen, The simplest atom, one proton and one electron. N-helium, slightly more complex, 2 protons, 2 neutrons, 2 electrons. Then trace amounts of lithium and beryllium. That was it. The entire periodic table consisted of 3 or 4 elements. Then these elements had very specific properties. They couldn't cool efficiently once heated. Here's why that matters. When gas collapses under gravity, it heats up. Gravitational potential energy converts to kinetic energy, to heat. This is unavoidable, a consequence of basic physics. But for collapse to continue, for gas to compress enough to form stars, that heat has to go somewhere. It has to be radiated away. The gas has to cool, and cooling requires a mechanism to convert thermal energy into light that can escape. By hydrogen and helium in their atomic form can cool but only above certain temperatures. The atomic hydrogen radiates efficiently around 10,000 degrees. Helium, similar temperatures. Below that, they essentially stop radiating, become transparent to their own thermal energy. Molecular hydrogen can cool at lower temperatures, down to a few hundred degrees. But molecular hydrogen is fragile, easily destroyed by ultraviolet light. And in the early universe, with the first massive stars blasting out intense ultraviolet radiation, molecular hydrogen couldn't survive in most places. Is one. Minimum temperature it could reach, around a few thousand degrees in most environments. And gas at a few thousand degrees is hot. The atoms are moving at several kilometers per second. They have a lot of random thermal motion. This thermal motion creates pressure that resists gravitational collapse. For a cloud to collapse, despite this pressure, it needs to be massive, have enough gravity to overcome the thermal support. The math works out such that the minimum mass for a collapsing cloud is proportional to the temperature cubed. Higher temperature, much higher minimum mass. With only hydrogen and helium, the minimum mass was around 1,000 solar masses, maybe as low as a few hundred in ideal conditions, but never much less than that. So the first stars were massive. That to be. The physics gave them no choice. But then those stars died. And in their deaths, they created something new. Oxygen. Neon. Magnesium. Silicon. Sulfur. Diron. All the heavier elements up to, and including iron, were created in the cores of massive stars through nuclear fusion. Elements heavier than iron were created in the supernova explosion itself, as neutrons flooded through the exploding star and were captured by atomic nuclei. And all of these elements were ejected into space, spreading outward in an expanding shell, mixing with the surrounding hydrogen and helium. Now, the abundance of these metals was tiny. Make eject 10 solar masses of heavy elements into a region containing 1 million solar masses of hydrogen. The metallicity, the fraction of mass in heavy elements, was perhaps 1 part in 100,000. That doesn't sound like much, but it was enough, because these heavy elements are vastly more efficient at cooling than hydrogen and helium. Carbon and oxygen atoms have many electrons, complex energy level structures, dozens of different transitions they can make, each one emitting a photon. Then these transitions happen at lower energies than hydrogen's transitions, meaning they can cool gas at lower temperatures. A carbon atom colliding with a hydrogen molecule can radiate away energy even when the gas is only a few hundred degrees. Oxygen, similar. Silicon, magnesium, same story. O metal-enriched gas can cool to much lower temperatures than pristine gas, down to 100 degrees or less, down to temperatures where the atoms are barely moving. And lower temperatures, the minimum mass for collapse drops dramatically. Instead of 1,000 solar masses, now you can collapse clouds of 100 solar masses. 10. Even down to subsolar masses in the densest regions. Suddenly, the universe can form small stars. Stars like our sun. Stars that will burn not for a few million years, but for 10 billion years. Stars that are stable, long-lived, capable of hosting planetary systems for ages. This is the dawn of population EE stars, the second stellar generation. They began forming wherever the first supernovae had enriched the gas. Expanding bubbles around dead population Earth stars. Proto-galaxies, where multiple supernovae had occurred. Anywhere the metallicity had risen above a critical threshold. And the character of star formation changed completely. Instead of forming one or two massive stars from a collapsing cloud, now you got dozens or hundreds of smaller stars. Instead of brief, brilliant lives ending in supernova explosions, now you got long, steady burning. Instead of flooding the region with ultraviolet light and destroying molecular hydrogen, the smaller stars were gentler, allowed molecules to survive nearby. A cloud of metal-enriched gas collapsing under gravity would fragment, break into smaller and smaller pieces as it compressed, each fragment becoming a stellar core. You can watch this process in molecular clouds today, regions like the Orion Nebula or the Eagle Nebula, giant clouds of gas fragmenting into thousands of stars simultaneously. But in the early universe, this was new, revolutionary, and it accelerated galaxy formation. Because population, E-stars are more efficient. They convert gas into stars faster, pack more stars into a given volume, produce more total light for the same amount of gas. And because they live longer, they accumulate. Population EA stars would form and explode within a few million years, so at any given moment, there were never very many of them around. But population E stars live for billions of years. So they build up over time, each generation adding to the previous ones, creating larger and larger stellar populations. This is what galaxies are made of, billions of long-lived stars orbiting together, creating a persistent luminous structure. Population EC stars were the match that lit the fire. But population EC stars were the fuel that kept it burning. And as more population EC stars formed and lived and eventually died, they enriched the gas even further. Each supernova adding more carbon, more oxygen, more iron. The metallicity crept upward. 1 part in 100,000 became 1 part in 10,000. Then 1 part in 1,000. And as it increased, star formation became even more efficient. Clouds could fragment even more finely. Even smaller stars could form. Day-positive feedback loop. Metals, enabling star formation. Star formation producing more metals. More metals enabling even more star formation. This is how galaxies grew, not smoothly, not steadily, but in a cascade of increasing efficiency as the gas composition evolved. And it all hinged on those first metals, those first carbon and oxygen atoms, spread by the first supernovae. Without them, the universe might still be stuck forming only massive short-lived stars. Galaxies, and Galaxies. No sun like stars. No planets with stable environments. No. The periodic table is not just a list of elements. It's the foundation of everything. Te chemistry, device, .kes civilization. And it all began here, in the enriched gas clouds forming around the first supernovae, in the transition from population E-et to population E-et, in the moment when the universe learned how to build small stars. The first generation had provided the light. The second generation would build the cities. Imagine standing at the edge of one of these early galactic cores. Though standing isn't quite the right word, there's no ground, no up or down, just space and stars and glowing gas. Above you, below you, all around you, thousands of brilliant blue and white stars blaze through the surrounding clouds. They orbit a common center, spiraling inward in a complex gravitational dance, their paths crisscrossing in 3 dimensions. The density of stars here is extraordinary. In our modern Milky Way, in our solar neighborhood, stars are separated by light years, vast gulfs of emptiness between each point of light. The nearest star to our sun is over 4 light years away. But here, in these early galactic cores, stars orbit just light days or light weeks apart, close enough that their gravitational fields constantly tug on one another, close enough that their combined radiation pressure shapes the entire structure, close enough that you could see them as disks, not just points, if you were somehow there to observe. This is what a galactic nucleus looks like in its infancy. Not yet the organized, stable cores we see in mature galaxies, but dense enough, massive enough, to begin establishing a gravitational hierarchy. The deepest wells, the very centers of these clusters, pull in gas from all directions. Material flows inward along spiraling trajectories, heats up through friction and compression as it falls. Some of it forms more stars. The densest cores of infalling gas collapse directly into new stellar systems, adding to the population, making the cluster even more massive. Some of it feeds growing stellar mass black holes remnants left behind by the first supernovae. These black holes, 10 or 20 or 50 times the mass of the Sun, lurk in the cluster center, accreting gas that strays too close, growing slowly but steadily. And with each passing million years, the gravitational well grows deeper. More gas falls in along the cosmic web filaments, channeled by dark matter halos toward this central concentration. more stars form from that gas. More Nyrule, more heat, more gravity. The gravitational potential deepens like a pit, being dug deeper and deeper into space-time. What began as a modest concentration of a few thousand stars grows into tens of thousands, then hundreds of thousands. These are the seeds of galactic bulges, the ancient hearts around which everything else will eventually organize. But they don't form smoothly, not steadily. Star formation in these early clusters happens in bursts. Here's how it works. Dot gas flows inward toward the cluster center, accumulates there, builds up in density and mass. But initially, it's too hot to collapse, heated by the radiation from existing stars, stirred by turbulence from supernovae, supported by pressure. So it just sits there, circulating, slowly cooling as the metals within it radiate away energy. And as it cools, it contracts, becomes denser, which makes it cool even faster, because denser gas radiates more efficiently. Runaway process, thermal instability. And at some point, a critical threshold is crossed. The gas becomes cool enough, dense enough, that gravity overwhelms pressure. Large sections of the cloud begin collapsing simultaneously. Within just a few million years, 1 million solar masses of gas collapses, fragments into thousands of pieces. 10,000 stars ignite almost at once. Their combined light floods the surrounding region. Ultraviolet radiation pours out in all directions, ionizing the remaining gas, heating it back up, creating pressure that pushes it away. Star formation shuts off abruptly. The remaining gas, now hot and ionized, can't collapse anymore. Then a pause. The newborn stars continue to burn, pouring energy into their surroundings. But the gas slowly cools again, and more gas continues to flow in from outside, accumulating, settling. And eventually, perhaps 10 or 20 million years later, conditions are right again. Another burst, another wave of star formation, then another pulse of light. These early galaxy cores flickered not with a steady glow, but with a rhythm, a cosmic heartbeat. Dot on, off, off. Each pulse brighter than the last as the galaxy grew. Each burst adding more stars to the permanent population. Each cycle deepening the gravitational well and making the next cycle even more intense. If you could watch one of these proto-galaxies over 100 million years in time-lapse, you would see it pulsing, growing brighter during bursts, dimming between them as the massive stars died, but with each cycle, the baseline brightness increasing, more and more long-lived stars accumulating. And these bursts had consequences beyond just forming stars. When 10,000 massive stars ignite simultaneously, they don't just produce light. They create a wind, stellar wind, driven by the radiation pressure of their combined light. Photons carry momentum. When they're absorbed by atoms and surrounding gas, they transfer that momentum, push the atoms away from the source. And with 10,000 brilliant stars all pushing at once, the force is considerable enough to drive gas outward at hundreds of kilometers per second, creating bubbles of hot, low-density gas expanding through the cluster. Then, a few million years later, those massive stars begin to explode. supernovae. Dozens at first, then hundreds. Their blast waves merging into a superwind. This superwind can blow gas clear out of the cluster, at least temporarily, inject so much energy that the remaining gas is heated to millions of degrees and expelled. But the cluster's gravity is growing stronger with each burst. And eventually, it becomes strong enough to retain gas even in the face of supernova feedback, to pull back gas that was expelled in previous cycles, to continue growing despite the violence. This is a critical transition, the point where a proto-galactic cluster becomes a true galactic core. Stable enough to resist disruption, and massive enough to continue accumulating material indefinitely. Gravitationally deep enough to be permanent, and once that transition occurred, the galaxy had a foundation, an anchor, a center around which everything else could organize. The gravitational wells were deepening, becoming more stable, no longer just temporary accumulations of matter that could be easily disrupted by a single supernova or merger. These were becoming permanent structures, anchors in the cosmic web, places where matter would continue to flow and accumulate for billions of years. The first recognizable galactic shapes were emerging from the chaos. But something else was happening too, something that would define the appearance of most galaxies for the rest of cosmic history, something that began as a subtle effect but grew more and more important as time passed. The gas wasn't just falling straight down into these cores. It was spinning. Rotation begins to matter. In the earliest moments, when gas first collapsed into dark matter halos, the motion was mostly random particles moving in all directions, some inward, some outward, some sideways. Double chaos onto Piketty. In A1 chaos was a pattern. When you average out all the random motions, all the particles moving in different directions, there's usually a tiny net spin left over, an infinitesimal angular momentum imprinted during the initial collapse or inherited from the larger scale tidal field. At first, this rotation was negligible compared to the chaotic turbulence. The gas was falling in from all directions, tumbling and colliding, its motion dominated by random velocities rather than systematic rotation. But as the proto-galaxy matured, as the most violent mergers became less frequent, something changed. The random motions began to dissipate. When gas clouds collided, their random velocities converted to heat, which could be radiated away. But the systematic rotation, net spin, couldn't be radiated away. That angular momentum is conserved. It has nowhere to go unless transferred to something else. Cash, no one. First Asian for tens of years, the random motions died down while the systematic rotation remained. And, as this happened, the rotation became more apparent in the structure of the galaxy. Gas falling inward didn't fall straight down anymore. It fell in spirals, its inward motion balanced against its angular momentum. And when it reached a certain depth, where the centrifugal force from rotation balanced the inward pull of gravity, it stopped falling inward and began orbiting sideways instead. This is how disks form. The gas can't fall all the way to the center because angular momentum won't let it. Instead, It settles into a rotating disk at the radius where forces balance. Not all at once. Not smoothly. The first galactic disks were nothing like the majestic spirals we see in modern galaxies. They were clumpy, chaotic, unstable structures, more like thick pancakes of gas studded with brilliant star-forming regions than the thin, organized disks of today. The gas in these early disks was hot and turbulent. Massive clouds of hydrogen, enriched with metals from previous generations of stars, orbited the galactic center in elliptical, overlapping paths. When clouds collided, they compressed and fragmented, triggering intense bursts of star formation. These star-forming regions were enormous giant molecular clouds containing millions of solar masses of gas, each one giving birth to thousands of stars simultaneously. The resulting star clusters were so bright, so massive, that they dominated the light from the entire galaxy. From a distance, one of these early disk galaxies would look nothing like a modern spiral. Instead of elegant arms traced out by orderly star formation, you would see a chaotic patchwork of brilliant blue-white regions scattered throughout a thick, glowing disk. Each bright patch was a giant starburst-R region, where gas density had reached a critical threshold and thousands of stars were being born at once. The disk itself was thick perhaps 1,000 light-years from top to bottom, compared to the razor-thin 100 light-year disks of modern spirals. This thickness came from the violent turbulence. Dat glows moved up and down as much as they moved in circles. Supernova explosions sent shock waves rippling through the disk, stirring up material and preventing it from settling into a thin, calm structure. And the disks were unstable. Massive gas clouds within them were so dense that they had their own gravity strong enough to disturb the orbits of surrounding material. These gravitational disturbances created spiral patterns, but not the long-lived, steady spirals of modern galaxies. Instead, these were transient features, AMs, that formed, persisted for a few tens of millions of years, then dissolved back into chaos as the underlying mass distribution changed. The clumps themselves, those massive star-forming regions, were remarkable objects. Each one might contain 10 million or 100 million solar masses of gas, compressed into a region just a few hundred light-years across. The density was so high that stars formed at an incredible rate, perhaps 1,000 solar masses per year, 10,000 times faster than star formation in the modern Milky Way. And because the star formation was so rapid and concentrated, these clumps produced tremendous amounts of radiation and stellar winds. The combined light from millions of young stars created radiation pressure strong enough to push against the surrounding gas, while supernova explosions injected energy and momentum. These feedback processes could actually disrupt the clumps, blowing them apart after just a few tens of millions of years. But even as individual clumps formed and dissolved, new ones were constantly being created by gravitational instabilities in the disk. So the disk maintained its clumpy appearance, with bright star-forming regions scattered throughout, constantly being destroyed and reformed in a dynamic cycle. Some of these clumps migrated inward over time, driven by dynamical friction as they ploughed through the surrounding gas. They would spiral toward the galactic center, eventually merging with the core and adding to its mass. This migration process was an important mechanism for building up galactic bulges. The cores didn't just grow through gas infall and in situ star formation. They also grew through the accretion of massive star clusters that formed in the disk and migrated inward. Over hundreds of millions of years, this process could transfer a significant fraction of the disk's mass into the central bulge. Yet, despite their instability and chaos, these disks represented something profound. For the first time, galaxies had shape. They had structure that persisted beyond the lifetime of individual stars. The rotation that had been imprinted billions of years earlier, during the initial collapse of dark matter halos, was now making itself visible in the distribution of light. The universe had discovered the disk, one of its most elegant and persistent architectural forms. And, although these early disks were messy and unstable compared to modern spirals, they contained the seeds of everything that would come later. The rotation was there. The flattened structure was there. The pattern of star formation, organized by orbital dynamics, was there. It just needed time to settle, to calm down, to evolve into the graceful forms we see today. But these young disk galaxies were not isolated structures growing peacefully in empty space. They were surrounded by neighbors, and those neighbors were about to play a critical role in their evolution. As the engine of early cosmic evolution, in the modern universe, galaxy mergers are relatively rare events. The most galaxies spend billions of years in relative isolation, slowly accreting gas and forming stars at a steady pace. Major mergers collisions between galaxies of comparable mass might happen once or twice in a galaxy's lifetime, if that. But in the early universe, when everything was closer together, when the cosmic web was still condensing into its current configuration, mergers were constant. Every young galaxy existed in a crowded neighborhood. Small proto-galaxies orbited around slightly larger ones. Groups of galaxies formed in dense knots where multiple dark matter halos converged. And the gravitational dance was violent and chaotic. Lofted one his transcedes and the common they were essential. The common they were essential. Ordnafel, ye easilize till I can fay. Good together the stop, but would not fall. It becomes the commons were not just giftless and word lever. Laughter on they of the two first on one work a dove soffits. To work you have comfort having communions from little us for the signals or put the plants utilizations. Because skin utoline is Romactus Bedoinania. They were the primary mechanism by which galaxies grew. The biggest galaxies weren't the ones that formed in isolation and accreted gas steadily. They were the ones that underwent the most mergers, cannibalizing their neighbors and growing fat on absorbed mass. When two young galaxies approached each other, the encounter was spectacular. First, their dark matter halos interpenetrated. Dark matter doesn't collide in the traditional sense. Particles simply pass through each other, their only interaction gravitational. But this gravitational interaction was enough to slow the galaxies down, to bind them together, to ensure that what began as a close approach would end in a merger. Not temp as the halos interpenetrated, gravitational forces began to distort both Tidal forces differential gravity across the extent of each galaxy, stretch them along the line connecting their centers. Stars and gas in the outer regions felt different gravitational forces than material near the centers, causing the galaxies to elongate, to develop tidal tails streaming out behind them. Then the gas collided. Unlike dark matter, gas has pressure. When the gas from two galaxies slammed together at hundreds of kilometers per second, it couldn't interpenetrate. Instead, it created enormous shock fronts, walls of compressed, heated gas that lit up in X-rays and ultraviolet light. The shock fronts were turbulent, unstable, shot through with dense filaments and expanding bubbles. Behind these shock fronts, something remarkable happened. The compression triggered star formation on a scale that dwarfed anything seen in isolated galaxies. Suddenly, gas clouds that had been too warm or too dispersed to collapse became unstable. The shock compressed them past the threshold for gravitational collapse. They fragmented and ignited in a cascade of starbirth. These merger-driven starbursts could increase a galaxy's star formation rate by a factor of 10 or 100. Regions that had been forming a few stars per year suddenly formed thousands. The combined light from all these new stars blazed so brightly that the merging system could outshine an entire normal galaxy. If you could have watched from a distance, you would have seen the two galaxies interpenetrating, and as they did, brilliant regions of star formation erupting throughout the collision zone. And it wasn't just stars that fed on the chaos. At the center of each galaxy, the black holes that had formed from the collapse of the first massive stars were also caught up in the merger. WS gas was funneled toward the galactic centers by gravitational torques. These black holes found themselves surrounded by a sudden abundance of fuel. The gas formed accretion disks around the black holes, spiraling inward, heating through friction to temperatures of millions of degrees. The accretion disks glowed brilliantly in X-rays and ultraviolet light. For a brief period, perhaps a few million years, merger might host not one but two active galactic nuclei, two small quasars blazing away as the black holes gorged themselves. Meanwhile, the galaxies themselves were being transformed. The tidal forces scrambled the orbits of stars, converting the ordered rotation of the original disks into random motions. The disks thickened, became more spheroidal. DIFTO was between two galaxies of comparable mass. The end result might be a spheroid with little or no remaining disk structure, an early elliptical galaxy. DIF the sixth guide with little or no remaining disk structure, GAN early elliptical galaxy. DIE1 galaxy was significantly larger than the other. The smaller one might be torn apart entirely, its stars scattered into streams orbiting the larger galaxy. Over time, these streams would phase mix, their stars spreading out into a diffuse halo surrounding the primary galaxy. This is how galactic halos formed, through the disruption and absorption of smaller satellite galaxies. And the black holes, spiraling inward toward each other, would eventually meet at the center of the merged system. They might orbit each other for millions of years, gradually losing orbital energy through dynamical friction as they gravitationally interacted with nearby stars. But eventually, inevitably, they would merge. The merger of two black holes releases an enormous burst of gravitational waves ripples in space-time itself, carrying away energy and momentum. In the early universe, these events happened countless times, each one a silent shout echoing through the fabric of reality. After the merger, a single larger black hole remained now, perhaps 100,000 solar masses, possibly more depending on the masses of the progenitors. And this merged black hole found itself at the center of a galaxy suddenly filled with gas. The merger had funneled enormous amounts of gas toward the center through gravitational torques. This gas formed a massive accretion disk around the black hole, feeding it at rates that might approach or even exceed the Eddington limit, the theoretical maximum rate at which a black hole can accrete before its own radiation blows away the infalling material. The resulting active galactic nucleus could blaze as a quasar, one of the most luminous objects in the universe, outshining the entire host galaxy by factors of hundreds or thousands. The radiation, winds, and jets from the quasar would carry enormous amounts of energy into the surrounding gas, heating it, driving powerful outflows that could expel gas from the galaxy entirely. This Ang feedback had profound consequences. It could quench star formation across the entire galaxy, shutting down the starburst that had been triggered by the merger. It could regulate the growth of both the black hole and the galaxy, establishing a relationship between black hole mass and galaxy properties that persists to this day. And it could enrich the intergalactic medium with metals, as the powerful winds carried metal-enriched gas out of the galaxy and into the surrounding space. The end state of a major merger was often a massive, quiescent galaxy rich in stars, formed during the merger-induced starburst, dominated by random stellar motions rather than organized rotation, hosting a massive central black hole that had shut down star formation through its feedback. These were the progenitors of giant elliptical galaxies, and they were being assembled through mergers in the first billion years of cosmic history. But not all mergers were equal. Mergers, collisions between a large galaxy and a much smaller one, had different outcomes. The small galaxy might be disrupted and absorbed without dramatically altering the structure of the larger one. Its stars would be scattered into the halo or accreted into the disk. Its gas might trigger a modest burst of star formation, but nothing like the spectacular starbursts of major mergers. And minor mergers were much more common than major ones, simply because small galaxies were more numerous than large ones. A typical galaxy might undergo dozens of minor mergers in the time it took to undergo one major merger, each one adding a bit of mass, stirring up the structure slightly, contributing to the gradual build-up of stellar populations. The early universe was a chaotic place, with mergers of all sizes happening constantly. Some galaxies grew primarily through major mergers, cannibalizing companions of comparable size and transforming into massive ellipticals. Others grew more gradually through multiple minor mergers and steady gas accretion, building up disk structures that survived repeated perturbations. Then the merger rate itself was evolving. In the densest regions, the protoclusters, where dozens of galaxies were forming in close proximity, mergers were incredibly common. Galaxies might merge multiple times in just a few 100 million years. These environments, the most massive galaxies grew rapidly, fed by a constant stream of merging companions. Less dense regions, mergers were less frequent, and galaxies had more time to settle between disruptions. These environments produced a more diverse population of galaxies, with disk-dominated systems more common than in the densest regions. The cosmic environment was already beginning to shape galaxy evolution, establishing patterns that would persist for billions of years. Nurbears weren't just a destructive force. They were constructive. They built the most massive galaxies. They triggered the most intense star formation. They grew the most massive black holes. They transformed gas-rich disks into stars. They established the morphological diversity we see in galaxies today. Without mergers, the universe would look completely different, filled with small, gas-rich, star-forming disks, with few massive ellipticals or quiescent galaxies. Dot collision and merger were fundamental to cosmic evolution. They were how the universe built its cities. And in the first billion years, as small proto-galaxies swarmed and collided and merged, the foundations were being laid for all the structures we see today. At the heart of every growing galaxy, a darkness waited. Black holes, remnants of dead stars, the collapsed cores of massive suns had existed since the first stellar generation. But in these early galaxies, something remarkable was happening. The black holes weren't simply sitting dormant. They were growing, feeding, becoming something unprecedented. They were becoming supermassive. The seeds were there from the beginning. When the first population IDC stars died, some collapsed into black holes of perhaps 10 to 100 solar masses, depending on the mass of the progenitor star and the details of the collapse. These stellar mass black holes were dense, compact objects, space-time singularities surrounded by event horizons just a few hundred kilometers across. But there may have been another pathway to black hole formation as well. In some of the densest, most massive dark matter halos, conditions might have been right for direct collapse. A cloud of pristine hydrogen gas, collapsing rapidly under gravity, might have reached such high densities that it bypassed the star formation stage entirely and collapsed straight into a black hole. These direct collapse black holes would be more massive from the start, perhaps 1,000 to 10,000 solar masses, giving them a head start on growth. Whatever their origin, these seed black holes began to sink toward the centers of their host dark matter halos. Dynamical friction. The gravitational drag exerted by surrounding matter caused them to lose orbital energy and spiral inward. Within a few tens of millions of years, they found their way to the deepest point in the gravitational potential, the galactic core. And there, they began to feast. Days Ars, lighter, from Stuntumagias, from supernova explosion, and itwell equal, you will itend cadios, ilenda, and can on center, dot kind trolled dire and verse chicofintra, novos somavia warrior counties, need the bonding. Instead, it formed an accretion disk, a swirling disk of gas spiraling inward toward the event horizon. Diand enema. An accretion disk is one of the most efficient engines in the universe for converting mass into energy. Probably Timisk into the Breppigen Swithiwas Dittib or 63 late lengthens of the art. 16. Deus gas spirals inward through the disk, Friction between adjacent streams of material converts orbital energy into heat. The temperature rises dramatically with proximity to the black hole, reaching thousands of degrees in the outer regions, millions of degrees in the inner regions, approaching 1 billion degrees at the innermost stable circular orbit just outside the event horizon. At these temperatures, the disk glows brilliantly in ultraviolet and X-ray light. The spectrum is characteristic, a thermal continuum from the hot disk, with broad emission lines from gas clouds orbiting nearby at high velocities. The O-total luminosity can be extraordinary, Li and high pink, black hole accreting at the Eddington limit. The theoretical maximum rate before radiation pressure blows away the infalling gas shines with a luminosity proportional to its mass. Azure lights with a luminosity proportional to its mass. Correspondingly, this bound of a luminosity can be extraordinary luminosity, can be extraordinary steady wilnapert. Or stellar mass. Black hole. Eddington, limited accretion produces luminosities comparable to bright stars. But for a black hole of 1,000 solar masses, it produces luminosities comparable to entire galaxies. And for a black hole of 1,000,000 solar masses or more, the luminosity can exceed that of all the stars in a large galaxy combined. This is what we call an active galactic nucleus, or ANG. And when the luminosity is high enough, visible across cosmic distances, we call it a quasar. The first quasars appeared within the first billion years of cosmic history. Observations from the James Webb Space Telescope and ground-based instruments have found supermassive black holes millions, or even billions of solar masses, already in place in galaxies, less than 1 billion years after the Big Bang. This is one of the great puzzles of early cosmic evolution. How did these black holes grow so large so quickly? The answer lies in the combination of favorable initial conditions and efficient growth mechanisms. The seed black holes may have been more massive than expected if direct collapse was common. And the growth rate could have been extraordinarily high in the dense gas-rich environments of early galaxies. Double-click hair, black hole growing at the Eddington limit, can double its mass in about 40 million years. Starting from 1,000 solar masses, it could reach 1,000,000 solar masses in about 400 million years, well within the time available in the first billion years. And if super Eddington accretion was possible, as some theoretical models suggest, the growth could be even faster. But there was another critical factor: mergers. Every time two galaxies merged, their central black holes eventually merged too. And each merger created a single, more massive black hole. If 1,000 solar mass black hole merged with another equal mass, the result was a 2,000 solar mass black hole. 10 such mergers could produce a black hole of over 1,000,000 solar masses, even without any accretion growth. In reality, both mechanisms operated together. Black holes grew through accretion between mergers, and then merged with other black holes when their host galaxies collided. This combination of accretion and mergers could produce 1,000,000 solar mass black holes within a few 100 million years, and 1 billion solar mass black holes within the first 1 billion years. And each episode of rapid growth had observable consequences. When a black hole accreted rapidly, the resulting GAN blazed across the universe. The radiation, winds, and jets from the Ang carried enormous amounts of energy into the surrounding gas. This Agon feedback heated gas, preventing it from cooling and forming stars. It drove powerful outflows, expelling gas from the galaxy entirely. It could even regulate the growth of the black hole itself by blowing away its own fuel supply. The winds from An were particularly important. Gas accelerated by radiation pressure or magnetic fields could reach velocities of thousands of kilometers per second, fast enough to escape the galaxy's gravitational well entirely. These winds carried metal, enriched gas from the galactic center out into the surrounding intergalactic medium, polluting it with heavy elements. Jets were even more dramatic. Summergan, material falling toward the black hole, didn't simply. Instead, magnetic fields threading the accretion disk and amplified by differential rotation launched narrow jets of material from the poles of the disk. These jets moved at relativistic speed, significant fractions of the speed of light, and carried enormous amounts of energy. When a jet ploughed into the surrounding gas, it created a shock front, heating the gas to tens of millions of degrees. The hot gas expanded, forming enormous bubbles that could extend far beyond the galaxy itself. These bubbles injected energy into the intergalactic medium over volumes spanning millions of light years, affecting not just the host galaxy, but its entire neighborhood. Dagnane feedback is now understood to be a critical regulator of galaxy growth. Fashionhead is gadding, not to disturn misneed Berlinofer. Protection police ex kayak. Fate jet region was covered. She began second anach night Japan. Call times. And formashed or a crew and unwedded Jufra joined. His jack redo what a true reship. 15 I should have grown for to venues fall. Come to the SS3 to guys. Without it, theoretical models produce galaxies that are too massive, form stars too efficiently, and differ significantly from observations. The energy injected by supermassive black holes, though small in total mass compared to the galaxy, is crucial in shaping galactic evolution. And this relationship between black holes and galaxies was being established in the first billion years. The black holes grew alongside their host galaxies, fed by the same gas reservoirs, shaped by the same mergers. And, through their feedback, they influence the rate of star formation, the distribution of gas, and the eventual structure of the galaxy. By the end of the first billion years, many galaxies hosted central black holes of hundreds of thousands or even millions of solar masses. The most massive galaxies, in the densest environments, might have hosted black holes approaching 1 billion solar masses, already comparable to the most massive black holes we see in the centers of giant galaxies today. These supermassive black holes were not passive passengers in galactic evolution. They were active participants, shaping, regulating, and in some cases dominating their host galaxies. The seeds planted by the first stellar generation had grown into monsters. And those monsters were learning to govern the cities they inhabited. Galaxies did not grow in isolation. Galaxy first billion years unfolded. The cosmic web became increasingly apparent. What had begun as subtle density fluctuations in the dark matter distribution had amplified through gravity into a vast network of filaments, nodes, and voids. The densest regions, the nodes where multiple filaments intersected, became the sites of galaxy clusters and groups. Here, in these cosmic traffic junctions, dozens or hundreds of proto-galaxies formed in close proximity, their fates intimately linked. This was the birth of cosmic neighborhoods. Consider a typical overdense region at this epoch, a node in the cosmic web, perhaps 10 million light-years across. Dark matter had been accumulating here for hundreds of millions of years, creating a gravitational well deep enough to trap significant amounts of gas. Within this region, dozens of small galaxies formed, each one a cluster of stars and hot gas, each one growing through the processes we've discussed: star formation bursts, mergers with neighbors, accretion from the cosmic web. But unlike the isolated galaxies that might form in the sparse regions between filaments, these galaxies were in constant interaction with their neighbors. The gravitational influence of nearby galaxies perturbed their orbits, stirred up their gas, triggered bursts of star formation through tidal interactions. And in the densest cores of these proto-groups, where galaxies were packed closest together, mergers were extremely common. The environment profoundly shaped galaxy evolution. The smallest galaxies, dwarf galaxies containing perhaps only a few million stars, orbited around larger siblings like moons orbiting planets. As they moved through the diffuse hot gas that filled the group, they experienced ram pressure. Their own cold gas was gradually stripped away by the pressure of moving through the hot medium, like a wind blowing away fog. This process, called ram pressure stripping, was particularly effective for small galaxies with shallow gravitational wells. As the dwarf galaxy ploughed through the hot intragroup gas at hundreds of kilometers per second, the pressure on the leading edge of its gas disk exceeded the gravitational force holding the gas in place. The gas was swept backward, forming a tail streaming behind the galaxy like a comet. Stripped of their gas, these dwarf galaxies could no longer form stars efficiently. They became ancient relics, their stellar populations aging and reddening with time, their star formation quenched by environmental effects. Some of these stripped dwarfs still exist today, orbiting larger galaxies as gas-poor satellites, fossils from the early universe. Their star formation shut down billions of years ago. Some dwarfs met more violent ends. Passing too close to a larger galaxy, they were torn apart by tidal forces, stretched and shredded until their stars were scattered into diffuse streams orbiting the larger galaxy. These tidal streams became fossil records of ancient mergers, sometimes persisting for billions of years as ghosts of consumed galaxies. If you look carefully at large galaxies today, you can often see faint streams and shells in their outer regions, the remnants of dwarf galaxies accreted long ago. The larger galaxies in these groups were engaged in a different dance. They orbited each other in complex patterns, gradually drawing closer as they radiated away orbital energy through dynamical friction. With each close passage, tidal forces distorted their shapes, pulled out tidal tails, funneled gas toward their centers. And over hundreds of millions of years, they would eventually merge, creating still larger galaxies at the centers of groups. This hierarchical assembly, small merging into large, large merging into larger, was the fundamental mechanism of galaxy growth. And nowhere was it more rapid, more efficient, than in these dense proto-groups. The central galaxies and groups could grow to millions, or even billions of solar masses within the first billion years, fed by a constant stream of merging companions. But the groups themselves were also evolving. WS Galax formed stars and exploded supernovae. They injected energy and metals into the surrounding gas. This heated the intragroup medium, the diffuse gas filling the space between galaxies to temperatures of millions of degrees. The hot gas glowed in X-rays, creating a diffuse halo around the group. And as the group's mass increased, its gravitational well deepened. Jesculins began a fall from surrounding filaments, was shock heated as it entered the deepened potential, adding to the hot intragroup medium. This created a self-regulating system. The group's gravity pulled in gas, which was heated by shocks and stellar feedback, which produced pressure that resisted further infall. The densest groups contained enough mass that they would eventually evolve into galaxy clusters' massive systems containing hundreds or thousands of galaxies, all bound together by gravity and embedded in an enormous halo of hot gas. Even in the first billion years, we can identify the progenitors of these clusters' regions with unusually high concentrations of young galaxies, all busily merging and growing. The contrast between dense and sparse environments was already pronounced. Dense ease charity. Galaxies in dense groups tended to be more massive, having grown through repeated mergers. Orgeslast lot galax now and Russia screamer placed, Kathstkins chest sporifive. It enters flex, Jack Jod, and like a corrected Ramina. Are you clear? Criviget first, and the minutes dorked. They also tended to be redder, their star formation quenched earlier by a combination of gas stripping, agvejkoveodes, time major depletion of their gas reserves through previous starbursts. Yet, rests of time because the watch high like one with aided expresses. If it with the vist jeffitness, skrivist it ovla. So if they're good division of the only novas, through figure birth that for one other, they teach lies, Tseka. The stellar populations were older, dominated by red and yellow stars rather than the blue young stars of active star-forming galaxies. Galaxies in the sparse regions between filaments, by contrast, could continue to accrete gas from their surroundings with less competition. They tended to remain smaller, bluer, more actively star-forming, though more isolated, less influenced by neighbours. These field galaxies, as they're called, could maintain steady star formation for billions of years, building up their stellar populations gradually rather than in the intense bursts characteristic of mergers. This dichotomy, the difference between galaxies in different environments, was already being established in the first billion years. The seeds of the morphology-density relation we observe today, where elliptical galaxies dominate clusters and spirals dominate the field, were being planted in these earliest cosmic neighborhoods. And the neighborhoods themselves were becoming more distinct. Groups were merging into larger groups. Jesculins were streaming along filaments toward the densest nodes, following the gravitational gradient toward the deepest potential wells. The architecture of the cosmic web was becoming more pronounced, more visible in the distribution of galaxies. If you could have mapped the universe at this epoch, created a three-dimensional map showing every galaxy and its environment, you would have seen a striking pattern. Most galaxies would lie along filaments, like beads on strings stretched across the cosmos. At the intersections of these filaments, bright clusters of galaxies would blaze dense concentrations where mergers were constant and star formation was intense. And between the filaments, vast empty regions, voids, would contain few or no galaxies at all. These voids weren't truly empty, they contained dark matter and diffuse gas, but they were severely underdense compared to the filaments and nodes. Danae all flowed out Voidsgruppen, creating a cosmic circulation pattern that fed galaxy formation in the densest regions while leaving the voids increasingly empty. This pattern, the cosmic web of filaments, nodes, and voids, is the largest scale structure in the universe. And its basic architecture was laid down in this first billion years, carved by gravity from the initial density fluctuations left by the Big Bang. The universe was becoming organized. Random was giving way to pattern. Chaos was revealing hidden order. Cosmic cities were forming neighborhoods. And neighborhoods were forming the first sketches of the cosmic metropolis that would eventually fill the observable universe. A transformation was underway. The intergalactic medium, the diffuse gas filling the space between galaxies, had begun the cosmic dark ages as cool, neutral hydrogen. But by this epoch, several 100 million years after the Big Bang, it was being fundamentally altered by the galaxies themselves. This process is called reionization, and it represents one of the major phase transitions in cosmic history. The first stars and galaxies produced copious amounts of ultraviolet radiation, photons energetic enough to ionize hydrogen atoms, stripping away their electrons and leaving behind protons and free electrons. Initially, each galaxy created only a small bubble of ionized hydrogen in its immediate surroundings, perhaps a few million light years across. The ionizing photons streamed outward from the galaxy, ionizing every hydrogen atom they encountered until they were eventually absorbed after traveling a certain distance. But as more galaxies formed and more stars ignited, these bubbles grew. They expanded outward at nearly the speed of light, ionization fronts propagating as fast as the photons themselves. And eventually, the bubbles began to overlap. This was a critical moment. When two ionized bubbles merged, they created a larger ionized region. And as more bubbles merged, the ionized fraction of the universe began to increase rapidly. Imagine a cosmic foam, with each bubble representing the ionized region around a galaxy or group of galaxies. That at first, the bubbles are isolated, separated by vast expanses of neutral hydrogen. But as the bubbles grow and merge, the foam becomes increasingly connected. Diamonds of neutral hydrogen shrink, becoming rarer, eventually reduced to isolated pockets in the lowest density regions. The transition from mostly neutral to mostly ionized reionization was largely complete by about 1 billion years after the Big Bang, though the exact timeline is still being refined by observations. Different regions reionized at different times, with the densest regions ionizing first because they contained the most galaxies, and the voids ionizing last. This created a complex, patchy pattern during the transition, with some regions already fully ionized while others remained neutral. But reionization was only part of the story. The galaxies were altering the intergalactic medium in other ways too. Every supernova that exploded in these early galaxies injected energy and momentum into the surrounding gas. DIF, the galaxy was small, with a shallow gravitational well. This energy could drive powerful galactic winds, blowing gas out of the galaxy and into the surrounding intergalactic medium. These winds were not gentle. Dot gas, accelerated by supernova blast waves, could reach velocities of thousands of kilometers per second, fast enough to escape even relatively massive galaxies. And because the gas had been processed through stars, it carried with it the heavy elements forged in stellar cores and supernova explosions: carbon, oxygen, silicon, iron. For the first time, the intergalactic medium was being polluted with metals. Initially, this pollution was highly localized. Each galaxy created a plume or bubble of metal-enriched gas in its vicinity, expanding outward as the wind pushed through the surrounding medium. The boundary between enriched and pristine gas was sharp at first, marked by a shock front where the fast wind collided with the ambient intergalactic medium. But over time, these enriched regions expanded and mixed with their surroundings. Turbulence at the boundary between enriched and unenriched gas stirred the metals through larger volumes. Then successive generations of galaxies enriched successively larger regions. By the end of the first billion years, much of the intergalactic medium, within filaments and groups, had been at least lightly enriched with metals. The metallicity was still very low compared to the interstellar medium inside galaxies, perhaps 1,000th or 1/10,000th of solar metallicity. But it was enough to begin affecting the future evolution of the intergalactic medium. The presence of metals changed the cooling properties of the gas, allowing it to cool more efficiently. And this would have subtle but important effects on how gas accreted onto galaxies in later epochs. The winds from galaxies also heated the intergalactic medium. Hot gas blown out at thousands of kilometers per second was shock heated to temperatures of millions of degrees. This hot gas would remain in the intergalactic medium for billions of years, filling the space between galaxies with a tenuous, glowing plasma detectable in X-rays. In dense groups and clusters, this hot intragroup or intracluster medium would become one of the dominant components by mass, containing more baryonic matter than all the stars in all the galaxies combined. Anion feedback played a crucial role here. When a supermassive black hole accreted rapidly, the resulting jets and winds could inject enormous amounts of energy into the surrounding gas, far more than stellar processes alone. The Theotopperhansel single powerful agni to heat the intergalactic medium in an entire galaxy group, preventing gas from cooling and forming new galaxies. Can explain, even one of you ahead self, yet the Alex actuation to get of. In a single powerful agnew galaxies, I galax and Califon at different agated. In two concept Greek found as admission. Didn't choose it even if a just distraction Jews. Elastic shrunk. This again heating may explain one of the puzzles of galaxy formation, why there aren't more small galaxies than we actually observe. Theoretical predictions based on the abundance of dark matter halos suggest There should be far more dwarf galaxies than we see. The missing galaxies may never have formed because feedback preheated their gas, preventing it from cooling and collapsing to form stars. The intergalactic medium was also being shaped by the cosmic web itself. Gas flowed along filaments toward nodes, creating streams of relatively cool, dense gas surrounded by a diffuse, hot medium. These streams were the highways along which gas traveled from the voids to the galaxies. The gas in the streams remained relatively cool, few tens of thousands of degrees, because it was dense enough to cool efficiently through radiation. But the gas in the lower density regions between streams was heated to higher temperatures by a combination of gravitational shocks and feedback from galaxies. This created a temperature structure in the intergalactic medium that mirrored the density structure of the cosmic web. Dense filaments contained cool gas. The diffuse medium between filaments was hot. The gas in the deepest potential wells, the centers of groups and clusters, was the hottest of all. This warm, hot intergalactic medium, with temperatures between 100,000 and 10 million degrees, would eventually contain the majority of the universe's baryonic matter. But in these early times, it was just beginning to develop. Much of the gas was still cool enough to emit in ultraviolet absorption lines, creating what astronomers call the Lyman alpha forest when we observe distant quasars. The intergalactic medium was becoming complex, heterogeneous, interesting. No longer just a smooth background of neutral hydrogen, it was developing structure and chemistry. They were being sculpted by the galaxies it surrounded. This sculpting had profound implications for future galaxy formation. The metal-enriched gas expelled by early galaxies didn't stay in the intergalactic medium forever. Much of it eventually cooled and fell back onto galaxies, either the same galaxies that expelled it or neighboring ones. This process, called galactic recycling or the galactic fountain, meant that later generations of stars would form from gas already enriched with heavy elements. The heating of the intergalactic medium also regulated future galaxy formation. Hot gas in groups and clusters was prevented from cooling and forming stars efficiently, explaining why massive elliptical galaxies, which had already formed most of their stars, became common in these dense environments. The hot gas creates a reservoir that galaxies cannot easily access, starving them of fuel for star formation. By ice-setting the initial conditions for billions of years of subsequent evolution, the events of the first billion years left an indelible imprint on the universe. The intergalactic medium became a record of those early times. Sea medium, shaped by the first generations of stars and galaxies, carrying their chemical signatures forward through cosmic time. The universe was no longer just galaxies separated by empty space. It was galaxies embedded in a complex, evolving medium, a medium they influenced and were influenced by in turn. The cosmic ecosystem was taking shape. One billion years after the Big Bang, the universe had been transformed. It was no longer dark. It was no longer simple. D was no longer dominated by isolated objects scattered randomly through space. Instead, it had become something recognizably modern, universe filled with galaxies, grouped into neighborhoods, connected by filaments, organized by the invisible hand of dark matter and shaped by the processes we've explored. Let us take stock of what had been accomplished in this first billion years of cosmic growth. From the death of the first stars, the universe had learned to build galaxies. Small halos of dark matter, enriched with the metals from stellar explosions, became the sites of efficient star formation. Clusters of stars accumulated in these halos, creating the first galactic cores. WS gas continued to flow inward along cosmic filaments. It brought angular momentum with it, and the first galactic disks began to form, primitive, clumpy, unstable, but recognizable as the ancestors of modern disk galaxies. These disks were sites of intense star formation, their light dominated by massive young stars, their structures constantly being rearranged by gravitational instabilities and feedback. Nermuse drove rapid growth. Small galaxies collided and combined, triggering starbursts and building ever larger systems. Each merger also brought together the central black holes, creating progressively more massive seeds that would grow into the supermassive black holes at the hearts of galaxies. The violence of mergers transformed disk galaxies into spheroids, mixed their stellar populations, and funneled gas toward their centers. These black holes, through their accretion and feedback, shaped their host galaxies. They regulated star formation by heating and expelling gas. They drove powerful winds that enriched the intergalactic medium with metals. And in some cases, they created quasars blazing beacons visible across billions of light years, marking the positions of the most rapidly accreting black holes in the universe. Galaxies did not grow in isolation. They formed in groups and clusters, their evolution strongly influenced by their environments. Galaxies in dense environments experienced more mergers, more interactions, more rapid growth. They also experienced environmental quenching mechanisms like ram pressure stripping, which removed their gas and shut down star formation. The cosmic web, that vast network of dark matter filaments, channeled gas toward the densest regions, while also defining where galaxies would form and how they would interact. The nodes of the web became the sites of galaxy groups and protoclusters. The filaments became highways of gas flow, and the voids became increasingly empty as gas drained away toward higher density regions. Between the galaxies, the intergalactic medium was ionized and heated by stellar radiation and galactic winds. It was enriched with metals, seeded with the chemical fingerprints of stellar evolution. Temperature and density structures developed, mirroring the large-scale structure of the cosmic web. The intergalactic medium became a complex, structured component rather than a simple neutral background. By 1 billion years after the Big Bang, the universe contained perhaps tens of millions of galaxies within the observable volume, number that would grow to hundreds of billions by the present day, but already substantial. These early galaxies were diverse in their properties, reflecting the different environments and histories that had shaped them. Surum was small, irregular dwarfs containing only a few million stars, the abundant but faint population that would eventually become satellites of larger galaxies or be torn apart in mergers. These dwarfs were scattered throughout the cosmic web, particularly along filaments, their low masses making them vulnerable to feedback effects and environmental processes. Knothos were more substantial, with masses of hundreds of millions or even billions of solar masses. These galaxies had recognizable structures, dense stellar cores, sometimes surrounded by rotating disks of gas and young stars. They glowed primarily in ultraviolet light, their spectra dominated by hot, young stars with spectral types ONB. Their star formation rates were high, converting millions of solar masses of gas into stars every million years. Day. Few were already massive by any standard 10 billion solar masses or more. These precocious giants had grown rapidly through multiple major mergers. They would become the cores of the most massive galaxies in the later universe, the central galaxies in rich clusters. Already, they were showing signs of environmental quenching, their star formation rates declining as they exhausted their gas reserves, and ag feedback became increasingly important. And at the centers of many of these galaxies, supermassive black holes had already formed, some already weighing millions or even billions of solar masses, far larger relative to their host galaxies' masses than their descendants would be. The early universe was, in some ways, an era of outsized black holes, a puzzle that continues to challenge our understanding of rapid black hole growth mechanisms. The star formation rate in the universe at this epoch was substantial, perhaps not yet at its peak, which would come a few billion years later during the cosmic noon, but already orders of magnitude higher than today. The universe was actively building its stellar mass, converting gas into stars at a prodigious rate. Most stars that exist in the universe today had not yet been born, but the foundations were being laid. Most of this star formation occurred in small to medium-sized galaxies, not in the most massive ones. The smaller galaxies were more numerous and had more gas available relative to their existing stellar mass. They were the workhorses of cosmic star formation, collectively assembling much of the stellar mass we see in the universe today. The reionization of hydrogen was nearly complete. Most of the intergalactic medium had been ionized by the ultraviolet radiation from stars and active galactic nuclei. The cosmic dark ages had definitively ended. Universe was permanently transparent to most wavelengths of light. The last pockets of neutral hydrogen survived only in the voids, in the lowest density regions furthest from galaxies. If you could have travelled through the universe at this epoch, you would have seen a cosmos vastly different from today, yet hauntingly familiar in its basic structure. Looking out in any direction, you would see galaxies, thousands of them potentially visible to the naked eye if you were in a typical region of the cosmic web. Most would appear as irregular, clumpy blue smudges, their light dominated by hot young stars with surface temperatures of tens of thousands of degrees. Here and there, a quasar would blaze, subtle point of light far brighter than any galaxy, marking the position of a rapidly accreting supermassive black hole. The quasar's light would be so intense that it would outshine its entire host galaxy, making the galaxy itself nearly invisible against the glare. If you could observe in X-rays, you would see the accretion disk glowing brilliantly, and perhaps jets of material streaming out from the poles. The sky would not be uniformly filled with galaxies. Instead, they would cluster along filaments, like cities along highways, creating a web-like pattern visible in the distribution of light. Following a filament, you would pass galaxy after galaxy, many of them in the process of interacting or merging. Tidal tails and bridges would stretch between them like cosmic artwork, streams of stars and gas pulled out by gravitational forces. At the intersections of filaments, the nodes of the cosmic web, you would find protoclusters, dense concentrations of galaxies, dozens or hundreds in relatively small volumes, the bright lights of the cosmic metropolis. The galaxy density in these regions would be tens or hundreds of times higher than average. Mergers would be ongoing everywhere you looked, with galaxies in various stages of collision and coalescence. Dammed between the filaments, you would find voids, vast regions containing few or no galaxies, truly empty on the largest scales, the dark neighborhoods of the cosmic city. These voids wouldn't be completely dark, they would contain diffuse ionized gas, faintly glowing in recombination lines. But compared to the brilliant filaments and nodes, they would seem barren. The intergalactic medium would glow faintly in certain wavelengths. The ionized hydrogen would scatter and emit light from recombinations, creating a diffuse background glow. Shock, heated gas and filaments would emit X-rays, creating a faint X-ray background. Then the metal-enriched bubbles around galaxies might show emission lines characteristic of oxygen, carbon and other elements, the chemical signatures of stellar death. This was a universe in transition, no longer the dark, simple universe of the cosmic dark ages, but not yet the mature universe of billions of years later. Day T was adolescent, chaotic, full of energy and growth. Star formation rates were high. Merger rates were high. Black hole growth rates were high. Everything was happening faster, more violently, than it would in later epochs. The transformation from stars to galaxies was complete. The transformation from isolated lights to organized cosmic cities was well underway. And the universe was ready to continue its evolution, to build larger structures, to refine its galaxies, to mature into the cosmos we observe today. But that maturation would require billions more years. The formation of giant elliptical galaxies through repeated mergers, the development of grand spiral galaxies with well-defined disks and spiral arms, the assembly of massive galaxy clusters containing thousands of galaxies, the peak of cosmic star formation during the cosmic noon, the gradual decline in star formation rates as the universe expanded and gas became more diffuse. The first billion years had laid the foundation. The cosmic cities had been built. The mechanisms of galaxy formation and evolution had been established. The relationship between galaxies and their central black holes had been forged. The cosmic web had emerged as the organizing principle of large-scale structure. Now those cities would grow, evolve, and diversify, creating the rich tapestry of galactic morphologies and environments that fill our universe. Spirals would develop elegant arms traced by star formation. Ellipticals would become red and quiescent, their star formation shut down by exhaustion of gas and Agon feedback. Irregular galaxies would persist as sites of ongoing chaotic star formation. New galaxy clusters would assemble through the hierarchical merging of groups. Massive elliptical galaxies at their centers would cannibalize smaller galaxies, growing to trillions of solar masses. The hot intracluster medium would grow in mass and temperature, becoming one of the dominant baryonic components in clusters. The universe's star formation rate would peak around 3 or 4 billion years after the Big Bang, during the cosmic noon, when galaxies were most actively building their stellar populations. Then it would gradually decline as gas was depleted, as feedback became more effective, as the universe expanded and made it harder for gas to cool and collapse. Dotka, our own Milky Way galaxy, traces its lineage back to this era. Tonsui. Somewhere in the first billion years, a small proto-galaxy was forming, accreting gas from the cosmic web, forming stars, merging with neighbors. Over billions of years, it would grow into the spiral galaxy we inhabit today, with hundreds of billions of stars, a massive central black hole, and a disk showing beautiful spiral arms. The Earth would not form for another 8 billion years. The Sun would not ignite for another 8.5 billion years. Dvors Wainaktislua of Zana, Sri Chand humans would not evolve to look back at this ancient epoch for another 13 billion years. But the foundations for all of it were being laid here, in the first billion years, when the universe learned to build cities. This was the end of the beginning. The universe had learned to grow galaxies. It had established the cosmic web. It had seeded every galaxy with a central black hole. It had enriched the intergalactic medium with metals. 60 teat had in metic langs and tikfa yot nov. Now it would spend the next 13 billion years refining and elaborating on these themes. The cosmos had ignited. The galaxies had assembled. The cosmic web had emerged. And looking forward from this billion-year milestone, the future was full of possibility. The seeds had been planted. The mechanisms were in place. The stage was set for billions of years of continued evolution. The universe had become a city of lights scattered at first, then gathering into neighborhoods, connected by invisible roads, organized by gravity's patient hand. And this city would continue to grow, to evolve, to become ever more complex and beautiful for billions of years to come. From the first stars to the first galaxies, from chaos to structure, from darkness to light, first billion years had rewritten the cosmic story. The universe had learned to build. And what it would build in the eons to come would be magnificent. But that is a story for another time. For now, we stand at the end of the beginning, looking back at a transformation complete and forward at a future unwritten. The cosmic cities had risen. The age of galaxies had begun. And the universe would never be dark again.